The broadcast is now starting. All attendees are in listen-only mode.
Well, good afternoon, everybody, and welcome along to DBA Fundamentals Down Under. My name is Warwick Rudd, and once again, I'm your host for this month's session. In this month's session, we've got Thomas Grohser talking to us about why you should use Column Store and avoid the mistakes that he has made. So this should be a fantastic session for us to follow along and take advantage of Thomas's knowledge, but also the mistakes that he has already learned from. Now, I will hand over to Thomas very shortly. I do have a couple of slides just as some housekeeping for this month's session. So first off, I need to say a big thank you to our sponsors, Century One. If you haven't already gone to Century One's website or know about Century One, make sure you go along to their website as they have some fantastic products available to you that can help you with your data platform workloads. Our second sponsor that we also have to call out to is DB Watch. Just like Century One, they also have some fantastic products on their website to assist you from your day-to-day data platform workloads. Just like this virtual chapter, there are many other virtual chapters available through PASS. If you haven't already seen those, make sure that you go to the PASS website, have a look for the other virtual chapters and look at those that may be of interest to yourself. Join up and you can get regular learnings just like today's session from industry experts. So with that, we'll hand over to Thomas for this month's session.
Okay, hello everybody. I hope you can understand me. Give me a few seconds to click on the right buttons to share my screen. Somehow, this is the share screen thing, I think. Really?
There we go.
Yep. Okay. Wait a second. Okay, so today I'm going to talk about cost of column store indexes and column store indexes in general for the next about 1 hour, and let's get started. I'm with SQL forever. It's 26 years this year, 26 years of SQL Server. I started with version 4.21. At that time, Windows was still 16-bit, and it was really hard to connect to the 32-bit app of Windows NT from your Windows 3.1 network. But we've came a long way since then, and for a couple of years, I'm a data platform MVP, and I usually get hired by rather larger corporations to build their infrastructure and help them get things on the road working for them smoothly. The one part here is what I'm talking today about is I was involved with a big hedge fund and they needed to audit every database operation someone was doing. So sounds simple, but then you look at the numbers and they had like 26,000 databases and there were several billion queries per day. So oops, we might get a lot of data. And then the question, how many years do you want to have like the records? And they said like 7 years. So when you multiply 6 billion to 10 billion of queries per day times 365 days times 7 years, it's a lot of queries. And storing them and all the associated metadata, like who did it, from where, from to, from what, sounds like a lot of data. So we were looking around and looking at page compression and other features that did not turn out to be sufficient. And then we pushed our eye on column store index, and it sounded great. And it only took us like 4 or 5 tries to get it right, or to get it as right as we have it today. We are still not 100% happy, but it's much, much better than the first 4 or 5 big mistakes we did. And back at the time, there was not much documentation available, so we learned by doing. And this talk will share this information. I will also talk about how column store works, then the big what to do and what not, and then you guys can ask me questions thing. We will break a couple of times for questions since virtual looks slightly different than in print. So, kind flashback, so we're all on the same page. How does row store work? Row store is the traditional thing that's around for like 30 years in SQL Server. And it basically, every row has a little header that tells SQL Server a bit information, what's in that row and what type of row it is and what to expect. And then each column is stored in kind of a binary format that SQL Server internally uses. And that's the way it is for a long time. And then we have the next row, which might be the same size, different size, depending on the data types, and so on. These rows go in a very random order on a data page. And then at the bottom of the page, there's usually this little slot array that points in order to where the rows are. And one page after the other is stored. So to get any information from any row or any column, you always have to load the whole page, then process through the page, process through the row, and get to the column that you need. Which, if you need most of the columns in each of one of your rows and in one of the tables, that's just fine. But especially in analytic workloads where you have very wide and very large fact tables, many queries only use a few of the columns actually. So there's lots of overhead things. And that was also the case in our scenario where we're basically having lots of columns, all the metadata, and normally we just would query by 1 or 2 of them. And that's the way. So how does column store the data? We have basically the same table. We have column A, and then column store stores first row, second row, third row, all the way to the nth row in one segment. And then the same goes for column B, C, D, and so on. Yeah? So instead of row by row, it stores the data column by column, hence the name column store. And a certain amount of these rows make up a row group. Right? Each column is called a segment, and then each 1 million rows is a row group. And then a second row group would have the columns again. So that's the way. If we take that aside, the way column store actually works is it now takes that piece here and puts it in a regular table. It takes the whole column, 1 million entries of a column, and compresses it into a var binary max and puts that in a regular table. And then it does the same with the second one, and then the next column, and so on till it's all done. Yeah? And this is a regular table, and you can actually query that table and look at the binary data. It doesn't give you any information because it's so highly compressed that you would never find your data again, and they are really good. So it's, if you, for example, in column A would have an ever-increasing integer, the whole thing takes about 1 byte in compressed form. Literally just telling it metadata, it's an ever-increasing value, go. Stuff like this. So it's really good. The problem with that table, and we will come to that later, and that's why I want you to remember, it's var binary max, so it's a blob. And blobs in tables will give us some grief over time that we have to deal with. If you want more details, there's a great talk from Bob Ward, and I will attach his slides when I share this one. I will attach a link to his slides. He has them on a GitHub, so no problem there. It's right there. And then there's a second great set of blog posts from Nico. I don't know where he's now, 160, 180, maybe 200 blogs about column store. So every nitty-gritty detail you can find there. Quick overview. Column store was first introduced in SQL 2012 in a practically unusable version. You had to put it on top of a regular table, so it didn't replace the table like clustered column store we're talking today does now. And it was read-only. So the moment you created that column store, you could not add or modify data in that table. So it was basically you load your data warehouse, you drop your clustered column store, you load your data warehouse, you recreate it, and then you hope that it works for the whole day and you never have to fix any data. So it's not very practical. In 2014, they added the clustered column store that becomes the table. So it replaces your either heap or clustered index with a clustered column store. And insert, update, deletes are possible on this one. But we will learn why we should avoid most of that. Then in 2016, it's now also possible to have the secondary index that is on top of a regular table to be modified. You could make filtered secondary indexes, so you're not indexing the whole thing, and non-clustered indexes on top of column store indexes, which is one of the mistakes. We use that, and that was a really big mistake. I'll get to that later. And then computed columns in 2017 that you finally could add to a column store, and in 2019 you can rebuild or build the indexes now in an online way, so you're not taking them offline during the rebuilds. Well, it's a quick history about column store. So the goal in the most projects when you're thinking about column store should be, how can we build a column store fact table that returns results quickly even when billions or trillions of rows are queried? And yes, column store scales into the trillions of rows. In my example right now, we passed the 3 trillion, and we will probably reach 4 trillion by the end of the year. 4 trillion rows in a single table, and it's growing by a couple of billion every day. So what's the solution to our problem? Column store is a great feature, but it needs our help. We must help column store to be as efficient as possible. Microsoft did something that you might or might not agree. It enabled column store to do much more than it was designed for, just to make it easier. But the problem is, when you take the easy route, you're disabling a lot of functionality inside column store, and we'll get to each one of them very soon. We must give it a nice physical database to exist in. And the reason for that is, in the beginning I told you that column store under the hood is stored in a regular table with a blob. That means if you don't put your column store on a file group that is big enough to grow, it's not too big, it's not too small, and you have an idea how you're going to grow it and how you move it around, because you cannot shrink a file in that file group. It's impossible. Even if you stop SQL Server, you completely disconnect, you're the only one running on that, and you run a shrink, it will not move the data around. It will move it, but you will not be living long enough to see the result. Why? I've talked column stores are big. So we're talking several gigabytes, maybe terabytes of data in one table. And then for every row to move to another page, what shrink does, it moves your pages to some other place. You have to do a full table scan of the whole thing. So if your underlying data is 1 terabyte in size and you want to move 8 kilobytes, it has to read 1 terabyte. And to move the next 8 kilobytes, it has to read the same terabyte again. Yeah? So shrink moves about a megabyte per week. Yeah? And that's just, the thing is, plan your database, it's important. You have to insert data, so row groups are created perfectly. If you just randomly put data in the column store, it will not be very efficient. You have to partition column stores by useful keys for your queries, not by something that seems to be easy. You have to choose your key very, very wisely. And you have to use data types that column store likes, not supports, likes. Very big difference. Yeah, column store supports a lot of data types. It's not a good idea to use them. So, the database. As I said, it's a regular table with var max. This means you cannot shrink. Sorry, I'm repeating myself. I forgot I had that slide. You can rebuild it in another file group. That's the only way, but keep in mind, moving lots of data around. Column store is for large sets of data. Unless you're having at least double-digit million rows, there's no point in using it. Yeah? I would even go far in our company. The recommendation is that you don't think about column store unless you have 100 million rows. Yeah, then you should start thinking about column store. Practically, we rarely use it unless we have at least 10, 15 billion. If we have the trillion rows, yeah, we definitely use it. So the important thing is you have to plan ahead so you not have to change the layout of your physical database files, because that will not work. I usually personally like to put a column store in its own file group and come up with a reasonable number of files, and every time they're full, I add another set of these files. Yeah, so usually I have somewhere between 12 and 24 data files. That has to do with our design, that we have our drives come in sets of 3. So we would either have 3, 6, 9, 12, or 24 disk drives in them servers. So 12 and 24 have a tendency to work out pretty well on these setups. So let's start how to insert data correctly. And this was the first mistake we made, because we just thought, okay, we insert the data as it comes along. We have a little, so we have these audits running all over the fleet, and then we have a little software that collects the data files, reads the audits in, and inserts the data into our column store. And it's great, but we didn't see any reasonable compression. And that's because we didn't meet the 2 friends we needed. Yeah. So this is your first friend, first of the 2 friends. This number, if you work with column stores, you will learn that number by heart. It's 1,048,576. It will haunt you, but it's a good thing that it does. For all the people that do math, if you take the square root of that number, it's 1,024. And that's the exact size of a row group. You remember we had these little columns, and I said roughly it's a million. It's not a million, it's 1,048,576 rows. So the way to make column store really, really go fast is to always insert exactly that number of rows in one go. Don't insert less, don't insert more. If you need to insert more, make sure it's a multiply of that. So twice that much, 3 times, 15 times, 10,000 times. That's fine. But don't insert the row less and don't insert the row more, because it will mess up your column store and it's hard to fix. If you insert less than 100,000, 102,400 rows, which is less than about 10% of that, SQL Server doesn't even bother creating a column store. It just behind the scenes creates a regular table and puts the rows in there and says, yeah, maybe I'll deal with it later. Right now, not. It's called a delta row group. So if you insert like 1 row at a time or so, yep, it all goes into a normal data store and you have 0 benefits of what you actually made the rest of the column store slower. Yeah. If you insert more, but less than the 1024 squared, then you get a row group by its own with whatever number of rows you insert. So if you insert 200,000 rows, you get a fresh row group, but you're wasting a lot of compression potential, because if you insert the next 200,000 rows, it doesn't go into the same row group, it goes into a new one again. And theoretically, if the 200,000 rows would have contained the exact same data, if they go into the same row group, it takes up 0 extra space to store the second 200,000. If they go into different ones, you take up the space twice. Yeah. So if you insert more than the magic number, then SQL Server creates a row group with the exact magic number, and then one with the remaining rows. So that's why if you insert exactly twice that number, it's just fine. But anything else, if you decide 1.5 million rows at a time, yeah, you create one with these many rows and then one with the remaining rows. And the second one, again, wastes compression potential. And not just compression potential, also, as we will learn later, potential to effectively eliminate row groups. Yeah, and just another way of saying it, 2 half-full row groups just compress less than 1 full one. You can clean up these mistakes. So if you ever accidentally insert the wrong number or you just have no other way of doing it, you have to rebuild the column store. Again, this is for very large sets of data, and rebuilding these indexes takes a lot of resources and might take more time than you have in your maintenance window. This is the insert architecture we came up in the second round after we learned that the first one is wrong. So we have all our little processing tier that creates the data. In our case, it pulls it from audits, but it could be anything else, any of your business apps that create data things. And these applications use the bulk insert API of SQL Server, not bulk insert command, but bulk insert API. .NET has it, Java has it, they all implemented it, to write the data into an in-memory OLTP table. And I get to the reason for that soon. And then we have an agent job that literally does a count star on the in-memory OLTP table every couple of seconds and says, hey, do I have that many rows or more? Yes, I'll grab the exact number of rows and put them in the actual column store. Yeah. So this one piles up the rows. Once it has all the rows it needs, it moves it in one big block over here and basically creates one new row group at a time. Yeah. And this works out great, especially since this part is all in SQL Server. So I guess, and the agents that create the data are outside. And the nice thing about this is we can have multiple of these. And since they're writing to in-memory OLTP, they're not blocking and locking each other. Yeah. This is the architecture we came up in version 2. It still is not perfect. The way we enhanced it is, we did not just wait for 1 million row. We waited for 1 million row per one more criteria. Yeah. So in our case, for example, each one of these audits came from a different machine. So we waited for 1,048,576 rows from one machine. And then we inserted it in the column store. The reason for that is now we had every row in that row group always belongs to one of our servers. So when we were querying the data later, we could take advantage of a feature called row group elimination. And we will talk about this in a couple of slides. Good. Before we go to deleting data, are there any pressing questions right now?
Not at this stage, Thomas.
Good. Moving on. Deleting data. There should be one thing. No. Never delete data. Why? A column store cannot delete data, but Microsoft implemented it anyway. And you remember when you insert just one row or so, that they create this table in the background where they store that row? Yeah, if you delete the data, they do the same thing. They insert a new row in a table, which basically says, hey, this row doesn't exist in the column store anymore. So the moment you start deleting data, every time you read your column store, Microsoft has to join that row store table with your column store table every time you ask it to do so. And that's a nasty thing. They try to optimize it by things, but it's still, it's really bad. Yeah. So if you have like the idea of deleting 1 million or a couple of billion rows, your column store becomes unusable because it literally has to join now two tables that are very, very large every time, and you will never finish. You might even run out of 10 TB space. Yeah. So every table, every query that runs, that reads data from the column store, once you deleted one row, will have to join with that table. Yeah. You can fix it again by rebuilding the column store, and that's the only way of getting rid of that. Yeah. So deleting data, not a good idea. But guess what? It can get worse than deleting data. You could have the brilliant idea of trying to update data. So who can guess what happens? What's an update? So you have your billions of rows in your column store, and you need to change one row. You can't delete it, but you can kind of by doing the trick with the extra row. So what SQL Server has to do is, because they can't update data in the column store either, doesn't work that way. So what they're doing is they're basically, an update is a delete followed by an insert of the new data. So what happens now is if you update one row, they create this background table for the deleted row, and now you have to join with that table every time. And then they insert a new row, which goes into one of these Delta stores and has to be joined as well and union together. So now, for updating one row, you created two extra tables that have to be joined and unioned with every select from the column store. That's why, again, don't update your data unless you really, really have to. And if you do, you have to immediately afterwards. Yeah. So data becomes a delete plus an insert, and they have to join every time. If you have to do that, you have to rebuild your column store, because otherwise the performance is going to tank so much. And we learned that lesson the hard way, because we, of course, when the project was new, we sometimes changed our mind how we're going to do something. And we thought, hey, yeah, it's easy. We just run a big update. We have a beefy server. Doesn't matter. After we ran the update, it ran all night, and that was fine. But then in the morning, we couldn't get any data out of the system anymore. So that's not. So another mistake we learned the hard way. So let's come to the fun part, selecting data. Column store only has one access method. Regular tables have many access methods. row lookup, scans, range scans, full scans, all kinds of things. Yeah, bookmark lookups, all awesome things you can have. Column store tables have one method. It's a full table scan. You need something from column store, it has to read the whole column store. Not the whole thing, so I'm kind of lying to you. To be precise, a full table scan with partition elimination. And this is why in the beginning I said you have to partition by something that's clever. Yeah. So if in your where clause you can eliminate or limit the number of partitions because you are having a where clause on the partition key, you can take a lot of work away. Yeah. So that's why you have to partition by very common search argument that narrows the number of partitions a lot. Yeah? So our first idea, which was horribly bad, was to go the easy route and partition by date. Yeah? Just a simple partition by date seemed like a good idea because most of the time when we query the audit data, the auditors have an idea which date range they want to do. What we didn't take in mind is that most of the time we want to join that column store table with some other information because that's how databases work. You join data. And the problem is if we limited the data down to one partition that is one day, we had about 6 billion rows, 6 to 10 billion rows per day in the column store. And if you join, since there's no index, the data is by definition not sorted. So the only way SQL Server can join a column store to anything else is by either sorting the data, which in 6 billion rows is a very bad idea, or do an hash join, and then has to build up a hash table of 6 billion rows, which is also not a really nice idea. And another big mistake that we had is we created 2 column stores in the beginning and had to join them. So 6 billion here, 6 billion here, 2 hash tables that turned out to be bigger than our TempDB. And we had about an 8 terabyte TempDB, and we couldn't join a single day. The problem is that the hash tables are not compressed. So you have super compressed data in the column store, and it looks like, hey, it's just a couple of gigabytes. But the moment you start joining it, it starts pushing that hash table, that hash join information into TempDB, and your TempDB blows up. So not a good idea. Yeah. You have to keep in mind there's a 12,000 partition limit in a table, but if you query the interwebs and have some experience with SQL Server, you know the practical limit is much more closer to about 3,000 partitions. Yeah? So 3,000 partitions gives you the chance of doing much more than just per day. Yeah. As I said, our first approach was doing a date, but then we came up with a surrogate key, combining several keys to limit our data more. As I said before, we had most of our queries were limited to one day and one machine. And what we came up with is we grouped machines into groups of machines and combined that with a date. Yeah? So that's how we made it more efficiently. So we got about 365 partitions per year times 7 years from the thing. And then we used the remaining number of bits that we have left to come to about 3,000 partitions to partition by a group of machines where we needed to limit the queries to. Yeah? So create as many partitions as possible, don't go much above 3,000, and pick something that really narrows down how much data you get out of it, because that's your first line of defense when you query data. You eliminate as many partitions as possible to not process them every time. Yeah. So another example would be you put together a year, a month, and a product group. Yeah? And that gives you a partition key. As long as you don't have too many product keys, product groups, you should be fine. Yeah? And this is old data warehousing tricks that are basically still applying to column store. And you can have larger than 3,000 values here. You just have to have 3,000, maximum of 3,000 different values here. So the second important thing, and another big mistake we made, is the data types. Yeah. So our first approach was, yeah, all the data that we collected, all the metadata, we just put it in the column store, and it does a great job in compressing them. So what had we had in there? IP addresses, machine names, the query text, lots of information, dates, times, types of operation done on the table, lots of things, about 160 different columns. And column store was doing a great job in compressing them. But when we ran queries, it took forever to get a result back. Yeah. So time to meet our second new best friend, and that's the number 8 bytes or 64 bits. Yeah. Column store is designed to deal with data that is 8 bytes or less in size. And we will get to the why under the hood later. But for now, it's if the data type is larger and takes more than 8 bytes, column store can handle it, but a lot of functionality gets disabled. And that's the functionality we get to in the next slides. Yeah. So column store loves data types. Which ones are these? Big int, small int, tiny int, datetime, datetime2, time, float, binary 1 to 8, character 1 to 8, nchar 1 to 4. It needs 2 bytes per character. Small money, and date. And that's it. Everything else needs more than 8 bytes. You can theoretically do a varchar, but that is weird. That's like a varchar 4, and there's no point in doing it. It's more efficient to put it in a character variable. So why limit everything to 8 bytes? If you do limit everything to 8 bytes, you can use the next awesome feature that column store can use. So we went from a full table scan, we eliminated a lot of partitions. So now we have more where clauses in the whole thing. And the first one is SQL Server can do filter pushdown. So you have a where clause somewhere in there, select X from table, my table, where Y between 7 and 25. SQL Server can put that where clause down to the storage engine and not even load data unless it fits into that range. Yeah. And the way it does that is it can do basically row group elimination. Yeah. We remember the underlying table that had the big binary max in it. It also has the min and the max value for each column in that row group. Yeah. So if one row group has only values 1, 2, 3, 4 in it, and you're looking between 7 and 25, the storage engine will not even return that row group to look at you for you, because it knows you need something that's larger than equal to 7 and smaller than 25, and I don't have that in that row group, so I'm not giving it to you. Yeah. That only works if you have filter pushdown. Why? Because the values, the metadata values, can only be 8 bytes and therefore are limited there. Yeah. So if in a row store, it doesn't matter, you have to load the whole row and scan through it anywhere. In column store, if it uses more than 8 bytes, it has to load every row group that's in the partitions that we need to load. Yeah. And That's just the very first thing. 8 bytes. It just returns only rows that match the criteria. The next one is aggregate pushdowns. Same thing as with filter pushdown. Yeah? The storage engine, instead of actually returning you the data, just aggregates it for you and doesn't return you all the individual rows for you to process. It just gives you what you ask it to do for. So for example, if you need a sum or an average from my table, in a row store, you load the page, you scan through every row, you take the value, you calculate your aggregate, and you move on. Yeah? In column store, if it's more than 8 bytes, you just load the one column, but you do the same thing. You run through every column and calculate the aggregate. If it's less or equal to 8 bytes, the storage engine just returns the aggregate, and all you have to do as the query is just add up or calculate the result from the individual row groups together. Yeah? And that makes a big difference in processing large amounts of data. Same goes, we already talked in the filter pushdown, the row group elimination is, we keep the dictionary values, and if a row group doesn't contain a value, it just doesn't get processed at all. Yeah. Yeah. And this is where I already said before, where we made the mistake. At the beginning, we inserted randomly how the data came in. And then we learned that it's good that we, within one row group, we group by one more value within the row group. And that in our case was the actual machine that created the data. So we had the partition key was the date plus a group of machines. And then in the row groups, we made sure that we knew that only data from one machine was in one row group. Yeah? And this is done right now by using the implementation of that it stays that way. Yeah. Even also we pre-sort the data, then by other columns we search a lot, or we know that have increasing values, because that allows column store to do compression more efficiently. Good. Before we go to batch mode, I do another call for questions.
Thomas, we just got a flashback. So with the insert of data, questions around, can you just explain the 1,048,576 rows again?
Yeah.
Do we insert data which is more than that in order to take advantage of the column store performance?
Every time you do an insert, it has to be that number of rows to be most efficient. You can insert any number, but you don't get efficiency. Yeah. If you insert exactly that number in one go, yeah. So that's why we choose the system of having that. Let me go back. This is why we choose that system. Yeah. This table is basically a staging table that piles up lots of data, and then we take exactly that number of rows in one go and insert it over. It's literally an insert into select, and then with a where clause at top, 1,048,576. Yeah. Again, if you do less or more, you just get a very badly organized column store. Yeah. It has to be that number. That number was randomly chosen by Microsoft. I'm guessing not randomly. They did some research on it, but why they didn't make it an even 1 million, I think it's that computers love powers of 2. So therefore, some calculations might be more efficient on powers of 2. But it has to be that number. Yeah. If a regular insert statement and a single insert statement can never produce that number of rows in one go, because even if you do multi-value inserts, it's limited by 1,000 rows. So you have to put it in some table first, and then move it from there into the column store. Yeah, that's what it is. Did this answer the question?
We'll say yes for the moment, and if they ask again, we'll revisit.
Okay, good. So now I have to find my slide again. Batch mode, that's the next one. So give it a second to load. Oops, here we go. So batch mode. So we had the whole table, we eliminated a bunch of partitions, we eliminated a bunch of row groups, and we already very efficiently calculated the aggregates on our raw data. The next thing that can speed things up is something called batch mode. And in batch mode, the difference is in normal row store, SQL Server processes one row at a time. Yeah? And that is really cumbersome. This is if you compare it with working in an office, and every time you need to process a file, you ask your coworker, can you hand me one file? And then the coworker gets up, goes to the file archive, pulls out one file, hands it to you. And then you look at it, put your rubber stamp on it, and hand it to the next coworker. Yeah? And then you ask the coworker again for one file. Yeah? That takes forever. But even with that, SQL Server is not that bad in processing normal row store. But in batch mode, instead of asking one file at a time, you ask your coworker, hey, give me 900 files in one go. Then he hands you over a batch of 900 files. You put 900 rubber stamps on it as fast as you can, and you hand them over to the next guy. Yeah. So when you look at the normal execution plan, it's row by row through the whole thing. Yeah. And with the batch mode, it's about 900 rows in one go. The exact number right now, and that's implementation, that's not set in stone, is 936. Yeah. So that eliminates a lot of back and forth between the operators in the query. Yeah? So every time data gets moved within SQL Server, it goes by about 900. Yeah? And that goes even for the operators that do calculations on the data. Yeah? And these are the ones that limit it to 900. Yeah? And I will explain that now. Modern CPUs have something called SIMD instruction sets, single instruction multiple data operations. Yeah? So how does this work? You can take 4 64-bit values and put them in 256 bits of memory, and then ask your CPU, can you basically add them up with the next 256 bits, but look at them as if they are 4 independent like float values. Yeah? And the CPU just does it. Yeah? And these are called vector operations. Yeah? So instead of working on one set of data at a time, these operations allow you to work on 4 pieces of data in one go. And that's why it's limited to 64-bit and the 8 bytes. And the 900 rows are, if you take about 64 kilobytes of memory, which is a memory page that they use for column store to deal with, and you have 8 bytes per entry plus overhead, that gives you about 900 rows, roughly. The metadata that they need to store with it then gives you about 900 rows for 64 kilobytes at 64 bits times 4 at the same time. Future will bring. CPU, Intel already has an instruction set that can do 512 bits in one operation, basically doubling this. I wouldn't be surprised if in a couple of years from now, SQL Server suddenly starts going either that they can do 128-bit values in column store efficiently, or that it suddenly becomes twice as fast overnight because they're processing twice as much data at the same time. Yeah? That's behind the scenes. It's not important. It's just sometimes people wonder why it's 936 rows, or roughly 900, and that's it. So how to handle data types that are larger than 8 bytes. And that's the part that we learned the hard way. Thing is, we put them in external tables and reference them through an int or a big int value as a lookup table. So instead of storing the name of the machine, which could be like a 16-character thingy, we stored a 2-byte number because we knew we're never going to have more than 65,000 servers, so we can deal with that. And similar with other things. Instead of storing the IP address as a text string, we converted the IP address into a 4-byte value and stored that binary value in column store, and then just had a function on the query that translated it back and forth. So this is what you do because you don't want to lose that. The problem is if you have a single column in your query that is more than 8 bytes, all the optimizations go away. Yeah? So we have them in other tables, and we look them up when necessary. When we query about it, we run the query first and then just have the where clause looking for the right number, for the right key. If it's for reports, we join on that, because joining a column store with a small external table works really, really well. Good. Archiving data. This is the one I'm still working on. I don't have a perfect solution right now. I cheated a little bit. We decided after 2 years that we're going to start archiving some of the data from the main server to a backup server. And that the first time when we moved about 3 trillion rows, we cheated. We took a backup and restored it on the archive server. That moved 3 trillion rows or 15 terabytes of data in one go. But now after that, every month, we have to move a certain amount of new data to the archive server. And that's a little bit tricky. Yeah. Column store really compresses good. Yeah. In our case, we have our average row is 168 bytes wide. That's our average row that we store. Yeah. It varies a little bit, but not much. Column store compresses that to about 3.5 bytes, less than 4 bytes. So inside column store, each one of our rows is less than 4 bytes. That's a lot of compression. It's awesome because several petabytes become 15 terabytes. The problem is if you select it out, so you're copying it through a linked server or you're BCPing out into a text file, it becomes its original amount of data again. And it's a lot of data that you have to push to a linked server. Because we figured out the minimum is we have to move like 1 row group at a time, because otherwise there's no point on the other side. So what I'm currently fighting with Microsoft is to give me a tool that can move a row group or a partition or whatever unit of information to another server without decompressing it, because the underlying table, I could just query and move the content of the underlying table, and that would be a couple of megabytes, gigabytes compared to hundreds of terabytes in the uncompressed version. And that's not available. I've successfully done it. The problem is after the next cumulative update, it stopped working because, of course, they have the right to change the internal metadata and implementation, and they did. And yeah, so that would be an awesome tool. So if you want to harass Microsoft people, tell them that's something we need, yeah? Yeah, so you have to move the data. So linked servers were one thing is, what we're doing right now as an intermediate solution, we wrote some C# code that basically streams the data from one machine to another. So we basically moved the linked servers to an external machine. It just works better than the linked server because we have an idea what's going on. We can look if it's working or not, and we can restart it if it breaks in the middle and stuff like this. Yeah? So archiving data is an unsolved issue, and I'm happy to update anybody as soon as I have a solution. But right now, I don't. Backups. So 99.9% of our database are right now column store. The rest, we have a couple of gigabytes of lookup data, but in a 15 terabyte column store, that is just a rounding error. Thing is, if we take a backup and we turn on, we tested this a lot because column store is already compressing like crazy. Yeah, so we're like, turning on backup compression is not going to help us at all, is it? And the answer is yes, it is. It actually still makes the backup smaller if you turn on compression by a significant amount. Yeah? So you're getting another 40% compression from the backups. And that's if you have, like in my case, 15 terabytes, saving 40% of that makes your backups way smaller. Yeah? So where are the limits right now? I don't know yet. So I haven't reached a limit that I've seen that it could not handle it. Yeah. So the largest column store, just above 3 trillion. When I made that slide deck, that was the case. We're at about 3.5 trillion, and it's working just fine. Yeah. It's about 15 terabytes in compressed version. So 168 data, and we compress about 32 to 1. The raw store would be about half a petabyte. And this comes in when we made the mistake at one of the intermediate versions. We thought that we would optimize the joins between our two column stores that we had instead of one that was denormalized. That if we put a regular B tree on top of the primary key, that we could then join much faster. Which in theory was correct. The problem is that that B tree was about 5 to 6 times larger than the whole column store and didn't help at all. It just either it wasn't ignored and the query optimizer didn't even consider it, or if it considered it, it had then the problem that it had to do a row lookup, and the way the row lookup goes is that it has to scan the whole row group where the row is in. Yeah? So that didn't help at all. Yeah? It actually made it worse. So where are the limits? In our 15 terabyte physical data size with 3 trillion rows, the majority of our queries are now less than 10 minutes for the most common cases that we could optimize the whole thing for. Yeah, we looked what are people trying to get out of the data, and in our company, this data is looked in a lot, especially by our security and risk people. Thing is, yeah. So count stars, sum, average, min, max, all these things are done through aggregate pushdowns. All the top queries they're running, we're making sure they're written in a way that aggregate pushdown can happen. Where date and some criteria that we have is done by partition elimination. It's like our server group thing is, and B, which is most likely limiting it to a specific server. So instead of just limiting it to the server, we're limiting first to a group and then to the server, and that makes it faster. It's done by row group elimination. And then we have a couple of filter pushdowns in usually another one where we like the source who did the query or something is limited down. Yeah. The group buys of a couple of columns is again done by aggregate pushdowns, because that's part of the aggregate. And then the whole thing runs in batch mode, since we eliminated everything that's more than 8 bytes. Yeah. And we did an index rebuild on every partition we had to delete or update data ever, and then stop doing it. So how we could stop doing it is one more change that we did, is the staging table. We are not moving the data immediately anymore. We keep a staging table and have data for about 24 hours in there. So we're basically giving it some time. So if we ever discuss something, find out something's wrong, we have basically 24 hours to fixing it in the staging table before it goes into the column store. And in most cases, that's good enough. Yeah, because the mistakes are usually just wrong configuration of new machines where some of the metadata might be wrong, and then we have rows in there that should not be there, and we just delete them in the staging tables. Yeah. So yeah, that's the presentation for today. This project was done by 2 people over a period of about 2 years. And in that time, one person worked on it about half of their time. And I was involved to about 10–15% of my time. But we learned a lot. We did a lot of mistakes. In the first 6 months, we had to throw away the data completely or build a new database and copy all the data over, because we made a couple of mistakes. First was we had 2 column store tables, not a good idea. We thought we are normalizing, like we learned to do the good way. So we got rid of that. We got rid of all the large columns that had, and we created regular lookup tables. We learned that we have to insert, that we can't delete and update. And with all that, in the 5th or 6th iteration, depending how you count, we now have a system that works. With one exception, we're still struggling to archive the whole thing. Yeah. So we haven't yet deleted data from the primary system, because we're not starting to do that unless we have a way to move data between the primary and the archive in a manner. We can move it with the current intermediate system, and we're doing it. We're keeping the archive at par with the primary server, but we're not confident enough that we could move the data back in a reasonable time frame if we need to, and therefore we're not. Good. Anybody, any questions?
So Thomas, this is going back. So in the case of a table that has both an integer and an nvarchar 500 column, when we create the column store index, so there should be row groups for the int column and a separate row group for the nvarchar column. Is that true? No.
So if you have 2 columns, one int, which is 4 bytes, and then nvar 500, don't use that data type. It's a data type they don't like. Yeah. But that is somewhere. The minimum is 2 bytes. That's when it's null, and the maximum is 502 bytes for that. Yeah. Or if it's nvarchar, sorry, it's double. So it's between 2 or 1,000 and 1,004 bytes. Yeah. No, 1,002. I'm tired. Sorry, it's late here. So that is a very bad column store index. Yeah. You get, if you just query that integer value, you get all the benefits. The moment you include your nvarchar 500 into your query, you're basically back to a full table scan. You might get partition elimination if you have partitioned by the integer value, but That's it. Then you're scanning the whole data every time. Yeah? You're getting the compression, which might be good, which might be better than page compression, but all the other stuff you're lost. Yeah? All the columns, each and every column must be less or equal than 8 bytes. Yeah, each one of them. Yeah. It has nothing to do how many rows you have. Yeah? The mistake here is already by choosing a data type that column store can't process efficiently. It can process it, but not efficiently. Yeah?
And that's where you mentioned about changing that and using an int or a big int and having that value in a standard table and using a row lookup based on that int, big int value to get the benefits.
Yes, I mean, of course, if this is unique for every row, then it makes no sense. Yeah, then there's just, you have no. But normally text values have a tendency to repeat themselves, unless they are some crazy JSON XML stuff where people try to store other stuff. So don't put that in there at all. But normally, if it's like country names, city names, zip codes, stuff like this, that's normally in text data a lot, or a product name or something. Yeah? You have to look at, this is a large fact table as you would have it in your data warehouse. Yeah? So it's usually very denormalized. Yeah? And for column store, it's great to have it denormalized as long as it's less than 8 bytes. If it's more than 8 bytes, then column store is not as efficient as it should be. And again, if you just tack on that one column and have 50 regular small columns, and then there's one wide, and it's used very infrequently, and that's fine. Yeah? But if it's used all the time, and if you only have 2 columns and one of them is that's not a use case for a column store. It's just not. I would not put that table in a column store whatsoever to begin with. It's just not efficient. You probably get better results with page compression and some clustered index on it.
Okay. Can you use a non-clustered column store index with a clustered column store index?
There's no point. It would result, you would literally duplicate that. There's no benefit. The benefit of the non-clustered is, so if you have your regular clustered index, yeah, then you can choose to put a secondary one on just a small portion of the columns, yeah, and that would give you a column store index, yeah. When you have the clustered column store, everything is already a column. So putting a second one on it would literally just copy that amount over here into the exact same thing. You're not gaining anything.
And when would you use a non-clustered column store index versus using a clustered column store index?
To this day, I have not found a place where a non-clustered column store made any sense. I haven't had a case. They might be out there. I just didn't stumble across one. Yeah. If you if you have a column store with lots of information in it, and you have many times where you only need certain columns out of it, but you don't want to transfer it into a column store index because you have many row lookups on that big table, yeah, then it might make sense to put a non-clustered column store on top of it. You use more storage, but you could then have the benefit of running large scans through the non-clustered column store and run your lookups through the regular clustered index. That's a case that I could see. I've never had that. In the financial industry, it's either long, large facts, or it's short, smaller tables. It's rarely something, just didn't have the case. Yeah, so that could be a case, but I never came across a practical example of having that. I'm not saying it's not there. There's use cases. Before there was clustered column store, it made a lot of sense. These days, it either makes sense, convert the whole table, or not. Yeah.
Okay. Well, with that, looks like we've got no further questions. So thank you, Thomas, for your time today. Fantastic session talking to us about clustered column store indexes and sharing your experiences and issues that you found along the way. Thank you, everybody, for coming along and joining us for today's session. This session has been recorded and will be available on the DBA Fundamentals archive site in the next couple of days. As Thomas mentioned, the slides from today's session will be available with the recording that you'll be able to have access to from the DBA Fundamentals archive site. Make sure to register for our next session, which is in a couple of weeks' time. We're now going to every fortnight, so there's plenty of opportunities for you to learn from some fantastic speakers that I have lined up over the next 5 or 6 months. Thank you, everybody. Have a fantastic afternoon, evening, morning, wherever you are.
Yep, thank you.